I'm the ezRA software guy, and so I am slowly ticking away, working on that, and hope to actually post up some new software soon. I'm concentrating on now we're getting fancy and have moving tracking telescopes. How can the collector record that as well? And can the analyzer then understand what the collector's talking about with different motions across the sky? If you could have some mechanical mount, point your antenna at a certain right ascension declination place in the sky, then the collector would understand what to do with it. Now, once you do that, you can look at a smaller part of the sky instead of the whole sky. And so there's a way to zoom in and look at your data in a certain small part of the sky instead of the whole sky. Stuff like that, along with lots of bug fixes and enhancements. That's it from here. Back to Rich.
Okay. Thanks, Ted. Let's see. And by the way, Ted, we give you an advertising announcement. We got a lot of new members on right now that have never been on before. Can you give a quick overview of ezRA and how they can get it?
Easy Radio Astronomy, or ezRA, or I pronounce it ezRA, is a bunch of software available for free up on the web. I'll put a link in the chat. That is my method of studying 1420 megahertz reception of data and what to do with it. First, you got to collect it. Then, once you get it, it's really weak. How do you pull that interesting stuff out of the noise? And then, what do you do when you get it? You could improve your data. You could plot it on the sky in several ways. You can get with enough data, you can start plotting the galactic arms. And then there's even one program to study the 3D shape of the galactic arms once you have enough data. All sorts of fun things to play with, lots of learning along the way. So I'll put a post on the in the web. There are lots of YouTubes, both at the introductory level and then deeper and deeper into it. It continues to be built, so it's always the documentation's always out of date, but I keep trying. My email's there. Come get me. Maybe you have data already, and there's ways to convert that data into a form that ezRA knows how to understand. I don't say it's the full solution, but it's what I have come up with at this point. I hope that makes it easier for others.
Okay, I highly recommend it. By the way, if you're just starting out, you can get a small microwave dish that you put just outside your patio, and you can start seeing galactic arms using just a couple components, real cheap components, and his software. So you're gonna just starting out, that'd be really fun to do. A lot of people are just starting to do that. Okay, Wolfgang.
Okay, one of the things I can briefly talk about is that we have resumed looking at a magnetar that goes back to a couple of years when we started looking at a specific magnetar that has re-brightened recently, and so we increased the cadence of observation on the magnetar just for the purpose of finding out more about it. The science driving background there is that there's some speculation that fast radio bursts might be magnetars. So we are collecting data to see whether that does support the idea or does not support the idea. So this is what we are busy with on the observation side with a 25-meter dish. And as far as our interferometry experiments are concerned, I would refer to Vanessa. I believe she's online as well, and she can maybe give you a quick update on what we do with our L-band interferometer.
Yeah, just because there's new people online, can you go over and give a quick overview of Astropeeler and what do you do there?
Okay. It's a radio observatory run by all volunteers. The main instrument is a 25-meter dish, which you can see as my background picture. And this is essentially equipped for L-band observation, and the prime work there is, besides the typical stuff like hydrogen, like stronger continuum sources like OH masers. Our main area of interest is pulsars and related subjects. The most interesting stuff that we are doing at the moment are fast radio bursts. These are the far away sources of short radio bursts of unknown origin. So we are trying to contribute to the science there to find out what these things are. Then on our premises, we have a 10-meter dish, which is intended for observation at 12 gigahertz and 22 gigahertz, aiming at methanol masers and water masers. Then we have two smaller L-band dishes, a 3-meter and a 2.3-meter dish, which we primarily use for experimenting around with and also to doing lab courses for various schools and universities. So these are the smaller instruments. And then what we have as our smallest instrument, it's a 1.2 meter dish, again L-band for hydrogen observation. And the specific thing about that is that it is mobile, so we can haul it around. It's on a trailer, and that is intended for working with schools. So we can go to a school and show them hydrogen line in radio regime. And then we have started to do interferometry stuff. There's one interferometer which has been around for quite a while. It's a Ku-band interferometer with a 10-meter baseline, which we have used for an all-sky survey. And the most recent thing that we are working on is a L-band interferometer with very small antennas. It's just essentially a circular waveguide made from a stovepipe. And the intention there is to build a experiment for students so that they can learn the basics of interferometry. And if you want to, let me put that in the chat, where you can find our website. Let me just put that there quickly. And there's information about our instruments and what we are doing and so on. Coming back to the interferometer, I just mentioned that one of from our team, Vanessa, she's working on that. That's her main task. She's doing her master thesis on this. And yeah, we're making slow progress, learning ourselves a lot about interferometry. And maybe I can hand over to Vanessa to tell a little bit about it.
Thanks, Wolfgang. Go ahead, Vanessa.
Hello. Yes, so we're building a little interferometer with 3 antennas at the moment. So we're having 3 baselines, so 2 longer ones and 1 shorter one. Yeah, we're still figuring everything out. So the last project was a little more on the phase matching and to have that corrected between the 2 different antennas of each baseline. And now I'm working a little more on the data analysis and how to work with the data that we actually got from the observations. So our main observation goal at the moment is to observe the sun. And maybe if we're sensitive enough, then we can also try other sources. But at the moment, we are limited to the sun. And in the beginning of May, we were also lucky to detect some solar flares in our region.
Okay. Can you re-show some of your results in your setup just for the new people?
Yeah, one moment. Okay, so at the back of the garage, we have our 3 antennas, which are mounted on a movable mount, so they can be moved along the pipe, and they can also be moved in elevation and a little in the azimuth. And we have 3 different baselines, so one short one here in the back, and then one longer, and then the whole east-west configuration. So mainly the interferometer is aligned in east-west alignment, but might be the case that we have a little offset of this east-west alignment. We're still trying to figure it out a little by measuring the transit point of the sun on each day. So the first slide was a very long baseline where we had some multipath interference. In the last couple of weeks, it was almost gone, this multipath interference. Might be the case because the grass now is longer, so we don't have that much of a ground reflection anymore, or maybe because we're working a little on the phase matching, that the cable lengths are improved, so we don't have this additional modulation anymore. Yeah, and here's a comparison between the different baselines, so the shorter one on the bottom and the longer one, and how that interferes with our fringes and how they change with the baseline. And that's the main part we're working on. And then what I've done the last couple of weeks is that I also got from this fringes the visibility and the phase, but we're still trying to figure that out a little, how that behaves while changing cable length and how that plays along.
Great. Good work. Okay. Any more from Osterpeeler, from Wolfgang or Vanessa? You guys got everything? Any questions?
Yeah. Can you remind me, are you just doing summing interferometry at this point, or do you have a more complex, like multiplicative interferometer setup?
That's a complex correlator that we are using to do the correlation. Yes. And the whole setup consists of, on the radio side, on 2 SDRs. Both of them, Ada and Pluto. We have reconfigured these to be dual channel. Now, the things that we have been working on is, if you have 2 times 2 channels, how do you correlate them against each other? And the way we do that is we put the middle antenna of our 3 antennas on both Plutos, on both SDRs, and then look for the autocorrelation function so that we can phase align the 2 Plutos. So that's the game that we are playing.
So you're essentially gathering just straight I and Q data that's able to be correlated, and then you can do whatever you want in post-processing then.
Yeah, that's correct. We just pick the IQ data, stream it from the 2 SDRs, and then, yeah, as you say, we can do what we want. Typically, we do the typical correlation thing by do a complex conjugate multiplication. We can also do an additive interferometer. That sort of comes as a byproduct, and whatever we can play around with it.
Yeah. Okay, thanks.
All right. Any more questions on this and interferometry in general? Okay.
I wanted to say, for Wolfgang, if you for the new people, is your paper on fast radio bursts accessible from your website, or?
Yeah, the latest paper, which was published in January in Nature, that's publicly available. I can put the link in the chat. I'll look it up and put it in the chat.
All right. Okay, thanks. Let's go to Edward.
Hi. So yeah, can you hear me?
Yep.
Okay, great. Well, that's working at least. So yeah, I have a couple small updates and observations. So can I share my screen?
Yes.
All right. There we go. Yeah. Can you see it? All right. So yeah, so I've been working a little bit on the telescope mount, which I was working on. So I told you about it last few meetings. So this is a mount for my 1 meter dish that I was making, and I run into some troubles with the on-step control board that I was trying to get to work. So I was trying to use OnStep, which is like an open source project for telescope mount control, to avoid having to code it, to do all the coding from the ground up. So unfortunately, this didn't go so well for quite a while, but now I finally seem to get it working. So I found some errors that I made in the configuration. So one particular one I found had to do with the drivers. So you need, of course, to specify which drivers you are using for the stepper motors. And yeah, there was an error in that I just didn't notice. And also that the people that that tried to help me with trying to get this to work didn't notice. So in the end, I found an example I found an example of the config.h file, so the configuration that you need to for the OnStep controller, that was sent to me by George Cushing, who built this board. And I somehow just completely forgot about this, and I just tried it out, so flashed it to the board, and well, it worked. So I was a bit surprised. So apparently there was no problem with the hardware. And one thing I found out was that the driver specified there in that config.h was TMC2200 quiet and not TMC2200. So I was like, okay, maybe this is the problem. I don't know if that matters. So I copied this over to my own config.h for my own mount, and it still didn't work. And I was a little bit confused, why doesn't it work? So I tried out some other things, and then I realized that the standard parking position that was specified was right at the celestial North Pole. And the way I was testing whether or not my OnStep was working was to let it start tracking. And of course, if you have an equatorial mount, even if it's pointed at the celestial pole, it's still tracking because it's still rotating around its equatorial axis. But for an L-tessiment mount, this is not the case. If you point it at celestial pole, it's just sitting still essentially. So yeah, this was another, well, not an error, but just something that I just didn't expect, and that was just really messing with the way I was testing this. Okay, can you see the next slide? Okay, great. So yeah, this is a little video that I made. So this is just showing this me testing the slewing function with Sky Planetarium. So here you can see I select an object. I say go to, and then you can see the motor start turning. So yeah, I was really happy to see this, to be honest. I still have to make some actual brackets and stuff and mount my motor on my mount and then see if it still works. But at least I'm making some real progress here. Okay, so next up, the actual observations that I did last month. So for this, I just still using the HEQ5 mount, of course, because well, the new mount is not finished yet. So I did some observations of Westerhout 49. So I'm still continuing the observation program for that particular source. So this is a spectrum I took at 22.2 gigahertz. You can see the spikes here. Those are the so-called masers. So yeah, for those of you that are new here, so my main focus is on so-called water masers. So these are a type of radio sources. They are essentially gas clouds in places like star-forming regions and in the atmospheres of red giant stars. And these gas clouds kind of act like naturally occurring lasers, but instead of visible light, they emit microwaves at very specific wavelengths. So essentially, like these objects are amplifying microwaves at a very specific frequency, and we can detect that. Really kind of cool bit of physics behind this. And what I'm particularly focusing on in the last 2 years, so-called water masers. So these emit at the frequency of the spectral line of water at 22.2 gigahertz. And some of them can be really strong, and you can detect them with a dish as small as 1 meter. So yeah, that's what I've been working on. Yeah, I'm making regular spectra of some of these maser sources, trying to see if there's any change or variation going on. So yeah, for Westerhout 49, as you can see, for the past few months that I've been tracking this source, not a whole lot of activity. There are no very big flares anymore in the main part of the spectrum that I'm monitoring. There's some like smaller activity here and there, but nothing major really. I also did a new spectrum of Cepheus A. So last time I observed this source was in September of last year. There's a big spike at around -9 kilometers per second and a smaller maser spike at maybe -30 kilometers per second. Although it's just barely above the noise, so it's not quite certain if it's real or if it's just like some RFI or something else. So yeah, the new spectrum from 26th of May, you can still see like this big spike at 9 kilometers per second. The one at -30 is like just outside of the range of the spectrum, so I'm not sure if it's still there or not. So this source seems to be a little bit brighter than it was last time, but no major changes in the spectrum. So finally, I did another observation of Orion KL. So this is the maser source in the Orion Nebula star-forming region. So I ran into some issues here with that even after subtracting my darks, so my off-target spectra, the spectrum was still not flat, as you can see here. So that's sort of like a parabolic shape to it. And I think this is just due to temperature drifting. So I made it in the afternoon and was heating up quite a bit outside. I tried to fix it by fitting a second order polynomial through the spectrum and subtracting that, but as you can see, it's still not very flat. You can still recognize like the main peaks, but it's not a very nice looking spectrum. So yeah, definitely need to do that one over again at some point. Okay, well, that's it for today. And yeah, if there are any questions, please ask.
Yes, Edward, take a look at that second order fit. Why don't you try a higher order polynomial? You see, it really, I did some LSR fitting in MATLAB and I was up to like a 6th order. Try a higher order there. See, right in the center, the orange line is a little high. If you go with a higher order polynomial, you might better match the detail there.
Yes, that's one way to do it. Although I'm always reminded when people suggest it of the very famous case of, I don't know if you remember, but there were some scientists they claimed to have detected phosphine in the atmosphere of Venus. And this was really quite unexpected. So they used a radio telescope, I think it was ALMA in Chile, to detect this gas, and they found way more than they ever expected. So there was some speculation, like maybe there's like some life form in the atmosphere of Venus producing this gas. And later they found out that like to process the spectra, they used like a 12th order polynomial to correct the background. And that introduced like some errors that eventually led like to the signal of the phosphine gas seeming to be way stronger than it actually was. there's
just
more
a
to the
thought.
story than that, but
You could try a couple order hires and
Yeah.
see how well behaved it is, and just see what your data looks like.
yeah, but generally, like, because I read it somewhere, I'm kind of careful with high order polynomial fitting. It can really throw in some errors if you're not careful.
All right. Anything else for Edward?
Yeah, I'll probably talk about this when I do mine, but I use polynomial fits to flatten my background as well, and I try to for the same reason you said, I try to stay at the lowest order that flattens just the region I care about. But sometimes I get up to fifth order if it's like an S-shaped curve or something, and it's not a nice. But usually I can get by with a second order, and it'll flatten it fine.
Okay, great. And I'm gonna make everybody jealous. I'm gonna drink coffee out of my SARA mug, which I got in the SARA gift store. So if and so just to make everybody jealous and go visit the store, go for it. And they're really nice, and they're actually pretty big. Okay, Alex.
Good afternoon. Well, I finally finished my my project. Let me share this with you. Been doing this for, let's see something here. Share screen. Here we go. Been working on this project for the past few months, and this all came about by me starting to get into building and designing these very lightweight portable disk yagis, and I wanted to have everything as a single assembly, to have all the electronics remotely and to be able to communicate with this thing over a fiber optic data link. Unbeknownst to me at the time, well, let's see. The AirSpy Mini is fairly temperature sensitive in that its spectral response changes. And in the past, I had it on the patio. It was in the shade. There evidently was some drift going on, but not nearly as significantly as being out in the sun. And even though I put a sun shield over the box, the temperature change over the day was fairly dramatic and gave me some pretty bad looking data. This is an example of non-compensated data in that the spectral shapes are all over the place. So the solution was to thermally stabilize this thing, and the way I did this was such. The AirSpy, the main thermal conductive path is through the SDR, or through the SMA shield, and so I made this 1/8 inch copper heatsink. It fits in there, and then that was installed over a pair of tech coolers, resistive heaters, and then a heat dissipation heatsink on the other side. And this is only partially enclosed. It's all enclosed in foam. So within this this box, there's some more pieces of foam, and then there's a cover piece that goes on top. This is the thermally stabilized SDR box, and some of the other parts of it is the bias tee to be able to drive the no electric LNA, and the thermal control has gotten fairly sophisticated. I have these little controllers of heat and cool, and they have thermal couples or elements that are packed inside this this foam box. This is what the control system looks like now. In that for cooling turns on the heatsink and the exhaust fan. It powers the 5-volt power supply to the techs, and I wanted to have some hysteresis, so I have the second controller set a little bit lower. So the cooling cycle runs between 82 and 86 Fahrenheit. The heat turns on at 71 and off at 75. And in addition to that, I have the intake box fan is on another thermal switch. So this looks like it it plays out pretty well. I've only had a chance to do this once because the weather's been pretty bad. The other hidden feature of this is the fiber optic transceiver, which is buried under everything else. But that was my goal, was to be able to transmit data over a fiber optic link, just to say I did it, and it works. The data that I took was somewhat accidentally close to the sun. There's a region of RA plus 20, DEC plus 20, RA around 650. That is a nice hot spot within the Milky Way, but also coincidentally right now, it's very close to the sun. So this drift that I got over 12 hours or so was actually correlated to sun noise bleed over. The novelty of this is that it actually spaced out the spectra. So for this case, I wasn't really interested in what the data looked like, but the quality of the stability of the spectra. And so the sun provided me this nice offset shift up and down over the 12-hour period so that you could see the individual spectra. And you zoom in on this low piece part here, the stability is pretty good. This is way down, and let's see. This is down, and I don't have that in dB yet, but it's very low amplitude, but stability between cool and hot is the same. There's no shift in the spectral response. And this is an easy MX plus B scaling shift to make these linear. But this shows that the system works. And if you do connect or convert it to a dB, stability is within something like 0.07 dB stability. So the system works, and I'm quite pleased with the quality of the data. Convert that to a spectrum, a contour plot of time versus velocity, and it looks nice. And this is the longer one. This is the 1.5 meter system. So what's nice about this is that it's very portable. Like I said, I have the 0.75 meter systems that I've been selling a few of them out there just to get a few out. I've made a few in the garage, so I'm slowly distribute these. But this makes a very lightweight, easily transportable system. And that's my software. Very quickly, again, this is the raw data. I measure the drift off of a region that is not affected by H1, create a corrected curve, calculate the LSR, correct for LSR, and then plot the results. So, project complete. Any questions?
Yeah, well, great work. That's for sure. It got me thinking actually, because my SDR is indoors, so that's not really my source of temperature drift. But in my case, it's the LNB that's outside, sitting in the sun on the dish. I was wondering, how heavy is this box, temperature controlled box that you made?
Well, the largest thing in it, Edward, is this fiber optic transceiver. I mean, you could make something like this. These are little $10 units I got off of Amazon, and so the actual temperature control part could be pretty small. And I had originally thought of, and even had designed a polarity switching relay for the techs, but then I was afraid I'd start driving this colder than atmosphere and start getting condensation. So it's a combination of two techs, and I found some 5-watt SMT resistors that are big enough to see and solder by hand, and I have 460 ohm resistors in parallel, which gives me about 4.5 watts of heat. So it's about 6 watts of cooling, 4 watts of heating. But you might want to, I mean, you might consider something like that. It's certainly not weatherproof, but the thermal stabilization seems to be working effectively.
Pretty cool.
I put all this slide set up on the SARA website. And so if you have any other questions, ask, but this is all the slides are already posted up there.
Okay.
Okay.
Yeah, this is Chet Mitchell. I had a question. Could you tell me or could you identify the boards you're using to drive the fans? And do they require another board to tell them what to do?
Okay, these are kind of nice. It's very simple. It's a relay output, single pole, double pole. That if it's too cold, it turns on the fan. If it's too hot, it turns on the fan. If it's cold, it provides continuity between these that you could turn on a heater. I'll find them on Amazon and tell you. And they come with a remote sensor. It's about 1/8 of an inch in diameter and maybe 1/2 an inch long, and they are embedded up in here. So it's a remote. They have remote sensing capability, and you can set the differential between turn on and turn off.
Mhm.
Hold on a second. Let me get some specs. So you can set the control point between 20C to 90C, and then the on-off between 1C, 1, 2, 5, and 10C. So I set it at 2C, which is about 4 degrees. And this seems to be to work pretty well.
Yeah, that's a nice design.
Yeah, it's real clean. You know, it runs off at 12 volts, and it automatically supplies 12 volts to the relay outputs. And so you just set in here what you want for temperature differential and the control point. And some of the others have push buttons where you got to reprogram them every time you power them up. These things you set and they stay. So I'll find that and put it in the chat. I even bought a couple extra ones for $10. It's a bargain.
Okay, thank you.
Sure. Any other questions? All right.
Thanks, Alex.
Sure.
Jason.
Okay, so I'm gonna kind of do, let's see, share screen. Is it okay if I share my screen here? Let me see here.
Go for it.
There we go. Geez, that's not what I wanted to do. Okay. Let's see if I can get this to, there we go. So I'm gonna kind of forward through this just to the, so similar to what Edward was doing, I've at the extremely low signal levels that I'm dealing with these extragalactic sources, I'm, you know, even when the system is fairly stable, it's not stable. You know, I mean, there's definitely curvature and slope going on. When I first started out, I was using just a simple linear fit, but as Edward pointed out, sometimes it can be, you know, more complicated curves. Usually I can get by with a second order fit, as in the case of my M33 data. Second order fit worked fine. M101, I ended up having to do a fifth order fit just because the shape of the curve was more complicated. And I can't remember which ones had I done the last time. I think I was up to maybe 5 or 6 at the last meeting. I redid NGC 2403 because I was a little dubious about the signal level that I was getting. It just seemed too high to be realistic, to be actual. And I went back and looked at, I looked at the individual 5-minute integration raw data sets just in a plot over frequency, and I could see that there was actually some EMI that just happened to be right where the one peak was, and it was giving me a false positive. And so I was able to eliminate those particular, because it was only actually a couple of snapshots that had that EMI in it. And so I was just able to delete those particular columns, and I still had plenty of integrated data, because that particular one is in beam over an hour each day. And so that cleaned up the spectrum a lot and brought it down into a more believable size range for the brightness that it was, as compared to M31 and M33, which were kind of those are kind of my gold standard, because I know those are absolutely real detections. As I'm getting down to smaller and smaller signals, it's becoming a little more fuzzy as to, am I seeing something real or not? I've added one additional one since we talked last. I did, I believe, get a positive ID on Homburg 2. I've still been unsuccessful on IC10. That's the only other one in that size range that I've been going after. I'm getting down to where there's none left in the survey that are large enough to be realistic to detect with my system. So I'm about to the end of what I think I can do realistically. But I have written up these results in a more comprehensive paper in anticipation of the Eastern Conference, and I will be giving a talk going over the entire process of the development of my dish through all its iterations, and some of the problems that arose and how I solved them, and how I've improved the data analysis process that I'm using, and the observation planning. So I guess that's all I got for today. Any questions?
Hey, Jason, since there's a lot of new people, can you go over sort of your setup and what you're actually, I think it's new to a lot of these people that you're actually trying to observe galaxies with Radio Astronomy. Just a quick overview.
Yeah, so this is actually what I have for my talk at the Eastern Conference, and it's kind of an abbreviated version of my paper. And so what I started doing was, this started a couple years ago. I had seen a survey in the hydrogen line of M31, which is the Andromeda galaxy, and I was just mesmerized by the double-horned spectral profile that you get from the edge-on view as you get the Doppler splitting of the single line, because it's spinning, right? And so I thought, wow, I wonder how small of a system is still adequate to detect this. And so that's how it started. What I ended up with after several iterations and 2 years worth of experimenting and coming up empty-handed, I eventually ended up with a 3-meter portable dish that's like a giant umbrella, basically. And it's the reflective material that I'm using is Faraday fabric. It's great stuff. It's not super expensive. It's very tough. It's very light. It's easy to work with. And I'm just using the electronics I'm using is just the Sawbird filter from Noelec, and I'm using a Smart T SDR from Noelec, which is similar to some of the other inexpensive SDRs that a lot of beginners in this hobby are using for hydrogen line detection. And then I'm using a loop feed with a shallow cake pan, a 6-inch cake pan, as the reflector, or as the I guess the back end. And then I'm doing my data analysis in Excel. And one of the goals was, I want to do this with a simple homemade setup, and I want to do it with drift scanning. I want to use a very low-tech system where I'm not tracking. I don't have any fancy stuff. And so I'm setting my as-L and leaving it. And my elevation is literally, I do the math, find out how high I need to raise the one side, and I put bricks and paving stones under it and use a ruler to measure it. I mean, it's really, really low tech. So most of the the trick is to have a good observation planning tool, and I've been using Stellarium, the actual iPhone app version, and I just set the field of view on the app to the beam width of my antenna, and I just set my location to my current location, center it on the area I'm wanting to look at in the sky, and just increment the clock until I see the object just enter and leave my field of view. And then I have my timestamps for where my main transit observation is. And then I just collect data before, during, and after. And then what I use is I use the before transit and after transit portions of the data as my calibration reference. And that does a couple of things. It helps compensate for some of the drift of the response of the receiver over time. And it also removes quite a bit of the local hydrogen signal if what I'm looking at happens to be fairly close to zero VLSR, so that so I can knock that signal down some and see more of the spectral profile, and it's not buried under the Milky Way. It doesn't get rid of all of it, but it does attenuate it quite a bit. So yeah, so I'm collecting. I just have SDR Sharp, the IF averaging plugin, taking snapshots about every 5 minutes, and then I gather all those files, dump them into an Excel spreadsheet, and I group them by pre-transit, main transit, and post-transit. I average those values together, and then I do a comparison of the main transit to the average of the pre and post as a calibration, and then I convert those values to dB using 20 log. And then as Edward was doing, I use polynomial fit to smooth out to flatten out the response curve of the receiver. And then what I end up with at the end, hopefully, is a recognizable spectrum. So here you see M31, and what you're seeing is just the upper portion, the portion that's more blue shifted, because the lower horn is actually buried under the local hydrogen signal from the Milky Way, so it's kind of difficult to see. And M31 is so edge on that the Doppler shifting is extreme on the both sides, so this spectrum is very wide, it's spread out. And so the bandwidth of my receiver is 3.2 megahertz, so I can only get about half of it. And so I'm getting the upper half here. I'm getting from 600-ish kilometers per second down to around 200 to 300. So I'm getting more than half, but definitely not the whole thing. M33, on the other hand, is more it's a little less tilted from our vantage point, so the splitting is less extreme. The entire spectral profile is narrower, and so it fits nicely within the flat part of my receiver bandwidth, and so I got a nice spectral profile for that one. That was probably my favorite of all of the ones, because it just comes out so clean looking. After that, my next one was dropping down in brightness an order of magnitude down into double digits of Janskys. So we're getting small. This is M101. And when I actually saw the two peaks for M101, I was actually surprised that I was able to see that at all. But that pretty much then opened up several more, because there's M101 is in the double digits, and then there's several in the very high single digits that I felt like were within range once I saw this, and that's where I started then looking for others. So this is M81, and then NGC 2403, and then M74, and then finally Homburg 2. And I believe there's only about one more that's detectable. There actually are about 3 others that are in the same range as Homburg as far as the signal strength, but unfortunately they're buried. They're very low velocity, so they're buried underneath the hydrogen signal from the Milky Way, and they're just, or in some cases, they're actually too close to other sources that are stronger. And because I'm using drift scanning and my dish is small, my beam width is too large and I can't separate them. And so so there's a few that I just had, I was disqualified from being able to detect with my system. There are a couple of strong sources in this size range that are too far south for my vantage point as well. They don't come up high enough above my horizon. So if I ever got a chance to take my system down into the tropics or the southern hemisphere, I could probably get a couple more. But so that's what I got for today.
All right, great. Anybody else got anything for Jason? Great work. And Ray, Jason's another one that if he had a 60-foot dish plugged into his system, could probably see a lot of galaxies. So
yeah,
we were talking about that too.
I was curious. What is your half power beam width on that 60-footer?
At 1420?
Yeah.
1420. Down around 7/10, I think, of a degree,
okay,
something like that.
Yeah, so that would definitely be
7,
small
8,
enough
10.
to separate some of those closer spaced mid-range ones. I mean, I could probably extend my detections down to another 10 or 20 objects with that dish, definitely.
Well, come out and see us.
Yeah. My girlfriend and I have been talking about taking a road trip out there. I actually, one of my good old friends from Oklahoma City, or from Norman, Oklahoma, actually originally, is John Ensworth, and I know he knows Ted. He might know a couple of you guys. I just found out last week that he actually knows you guys. So that's another reason to go out there and see him. I've not seen him for several years. So
yeah, we do have the 1420 feed up right now, and we've also modified it for 1600 megahertz, and we have not detected anything there yet, but we've only tried once. So 1420 works great.
cool. Yeah, I definitely, that's on my agenda for some time in the near future. So I'll be in touch, definitely.
Very good.
So Ray, now you're on, and maybe setting you up where you can take a few minutes to find some slides. Can you give an overview of DSES and the Plissner site?
I do not conveniently have that. No, I'm sorry.
Okay. All right. Maybe next time.
Okay.
All right. Let's see. We got a new student member. Is it Celsius? Are you on? I know he's on. Question if. Okay. Well, let's go to somebody else. John Brooks.
I'm here. Can you hear me?
Yeah.
Hi. Well, my name's John. I'm a ham N9ZL. I'm on the microwave bands, and I'm also an optical amateur astronomer. So I thought that this might be an interesting combination of my two hobbies. So I'm just kind of checking out what you guys are up to and seeing if there's anything I might be interested in.
Well, I think that's how a lot of us started as hams, and then we found out that radio astronomy is actually really hard, and taxed our technical abilities, and now we're hooked. So, welcome to the hobby.
Thank you.
Okay, Preston.
Good afternoon. I guess it's afternoon here anyway. I decided I needed to bolster my theory a little bit, so I've been reading some basic astrophysics. So that's what I've been doing.
Any recommended texts you would like to recommend?
Well, I've been reading. This is on an undergraduate level. I think it's Astrophysics for Physicists. So.
Okay. All right. Okay. Thanks, Preston.
You're welcome.
Jack. Jack Lobinger.
Yeah. Yeah, I know there were a couple of questions, or there seemed to be a couple of questions about being able to read antenna position over a link or programmatically to be able to put into programs, calculation, that sort of thing. That's precisely what those articles that I wrote back in 21 and 22. I guess it was June or April, something like that, of 22 and September of 21, I think, that put in, I had those articles about a tracking system. And of course, part of the tracking system was a system to read position out from encoders and be able to make that encoder position data available over a link. In my case, it was over a fiber optic link into my lab area where I had the actual positioning program. But anyway, if anybody has any interest in trying to read out position from encoders on a mount of any kind, I'm more than willing to share that information on how I did that. Past that, that was all the tracking system that was represented in those articles was basically on a gap control algorithm for being able to position the set point or the altitude and azimuth or right ascension and declination against the encoder position and control it within a gap because it was turning the drive motors on and off, that sort of thing. Since then, I've been working on a servo-based system using DC servos and PID-based servo controller made by an outfit in Italy called Solo. And with that, and because of the Hall encoders on the brushless motors, servo motors, you can get some incredible accuracy, probably accuracy that's better than the gearing of the mount. I've been working on got the azimuth part of that designed and done, and it's all using pretty standard components. And right now I'm working on the elevation part of it, and that's a little different because most linear positioners, which is linear actuators, which I've used in the past for doing the elevation control, don't have any kind of that sort of feedback, closed loop feedback. But in the case of what I've put together here, it's basically using the same servo brushless encoder based motors to be able to make a linear actuator that then gives me that same kind of accuracy. So I'm working on that part of it, and that one's not quite finished yet, but the azimuth part is, and it's got some pretty decent positioning capability. A lot better than the gap control that I was using with the ones that I wrote up in the articles previously. So that's what I've been working on.
Okay, any questions for Jack? He is pretty good at this mount systems. Okay, thanks, Jack.
Yep.
Skip.
Yeah. So, well, I don't really have anything to share. I've been working on the paper for the conference, writing a lot of software. There's quite a bit of checking I need to do. Taking a lot of data for about 90 days with the interferometer, 2 elements. So just a quick description. I've got a 2-element interferometer here on my farm. They're each 10-foot dishes at the elements, and I'm using a digital system to look for very narrow band pulses. So these are 3.7 hertz bandwidth pulses in a 50 megahertz occupied bandwidth, overall bandwidth. And I capture data 24 hours a day, and then I use post-processing to look for pulse pairs. So these are pulses that are very close together in frequency and have a sufficient SNR that they exceed the SNR threshold. And then I examine those in post-processing, and I look for directions in the sky where pulse pairs are present. So the idea is that it's kind of like a communication signal when you have a combination of signals that are narrow band and have using the same bandwidth of 3.7 hertz. So that's what I'm doing, and so I have about there was about 61 days of data that I put into the last archive paper. You can see that if you Google my name with archive, you can see that. And then the update I'm going to do for the conference is to try to replicate that observation that I got back then and see if there's any statistical significance to the pulses. Okay, so that's it. I guess that's all I've got.
Okay. Skip has also been in charge of the 40-foot dish at Green Bank. When people come to Green Bank and they want to go use that, is there anything they should study up on in terms of how the system's set up? And
well, I guess I don't think so. I mean, I think that it's always good. I really like this book here. I think my video is on. This is a great book. Just to study up if you want to get some background. And the 40-foot user's manual, I think is on the web, on the Green Bank page. There's a link to it there. It might be the older edition. There was an older edition, and I don't know if the new one got put onto the web, but that might be a good thing to study. And yeah, the evenings are all available. I'll help, although almost everyone who goes there nowadays, knows all of it. Some have been there many more times than I've been. But anyway, okay, yeah, I'll be glad to help.
Okay, great. Thanks, Skip. Let's see. I've got VI's phone. Who's that?
Yeah, my name's Viola Sanchez. I'm a pretty new member. I started doing the Radio Astronomy program for the Astronomical League. So I had to buy a few things from your website, and thought I'd join and learn a little more about it.
Great. Yeah. Some of us gold members, Astro League radio astronomers. So you've taken over the program, huh?
No. I'm just doing it.
Oh, you're doing it. Okay.
Yeah, I've done 2 of the 4 so far. So I'm still working on it.
Well, the hardest one is hydrogen, and I think this team has made it one of the easiest ones. So I think you could have a great start. Okay, thank you, and check out the YouTube channels, and if you join the SARA, you can get the journals where people are going over how to do all this stuff.
Great, thank you.
All right, thank you. Ellen. Helen, are you there? Okay, we'll go to Chet.
Hi, it's nice to be here with you. I'm a brand new member of SARA. I just joined in March, and my big project right now is I'm building one of those Despira horn telescopes with the wooden base and the foam thing, and that's been good. It's been a very stretching experience, and I'm looking forward to trying to do some stuff with it, and then just kind of learning more about the hobby. I did want to say, Jason, I'm really impressed with the fact that you can pick up data from other galaxies with a 3-meter telescope. That's very, I wouldn't have thought that would have been possible. So that's very interesting. Yeah, it's nice being here with you. And I plan to start coming to the Zooms every month.
All right. I'm sure I'm going to ask some questions I know everybody else is going to ask for new astronomers. What kind of antenna? Well, you already said the kind of, you're building a horn. You got an LNA, a receiver, software. What else you got?
That's I'm following the plan from West Virginia University, and I'm using a Sawbird 2 for the LNA, and I bought a AirSpy R2 to be my software-defined radio. And I'm currently trying to work with the spectrometer software to get it to compile on Linux. I think I've had a problem. I think I figured out that this software really wants new radio 3.8, not the 3.10.11 I've got. So I'm hoping to get that straightened out in the next couple of days.
Okay. Yeah, we'd love to see if you get some results. We'd love to see them.
Yeah, definitely.
Chad, I can confirm that the West Virginia University software, the spectrometer software, requires an older version of GNU Radio. That's correct.
Okay, that's helpful. I'll go ahead and uninstall the current one and install 3.8 and see if that works. Okay, thank you.
All right. Okay, thanks. Wendy.
Hello. I'm not doing anything because I'm trying to move. So I'm trying to finish up all my old projects and throw things away so that I can move. So for me, this is a break. I get to listen to you guys and guys and gals, and then read myself to sleep at night on journals and stuff. So that's about all I'm doing too.
Okay. Well, get a good night's sleep reading the journal. I'm sure you will.
Well, it beats staying up late at night.
The new journal will be out next week. It's in review right now by the board. Board of directors reviews the journal after I stick it together, and so that's well on its track to be out by next week. And we'll send if you're a member, you'll get an email notice with the link when it's out. Okay, Dimitri.
Hi to all. Just today, I visited our local millimeter waves man. Just a moment. It's his dish. His dish. Sergei Zhutyaev, Radio Whiskey 3 Bravo Papa, 2.4 meter dish. He is used for millimeter waves. The dish works well up to 50 gigahertz, and a bit worse in 7680 gigahertz. He was the first who received moon-bounce echo at 76 gigahertz. There was no two-wave exchange in radio at these frequencies at 76 gigahertz. Some Americans heard him at 76 gigahertz, but no two-way exchange. And this dish works up to 134 gigahertz with correcting subreflector, Gregory subreflectors. He especially designed it for using for high gigahertz, but the dish works well and works well for lower frequencies than 50 gigahertz. And today I visited him with my antenna unit for 6.7 gigahertz for methanol misers receiving focal length and size of dish is well to realize very high aperture efficiency, about 0.7. Calculated efficiency with this dish and my feet is more and 0.74 for this feet. And we were lucky to receive to obtain and receive first light from this with this dish at 6.7 gigahertz. This is spectrum. This is the screen of my receiver. W3 masers at 6.7 gigahertz appears maser bump appears very quickly, less than 1 minute integrations, and I think for the first light is very lucky. That's all for today. Thanks.
Any questions for Dmitry?
Dmitry, did you write that VI?
Please again.
I said, did you write that National Instruments virtual instrument panel software?
This is LabVIEW software. I wrote this program by my hands. This is my software, and I wrote this code more than 6 years from 2080, and this works well. Sorry, I did not use any.
I've written some things.
I did not use the other programs.
I've written some software in LabVIEW. That's a pretty good accomplishment. That's a fairly complex VI.
LabVIEW is my language, and I work with LabVIEW very, very long time.
All right. Okay. Any other questions for Dimitri? All right. Thanks. Good work.
Oh, thanks.
Okay. I got a Win Farrell.
Hi there. I've been on a couple of times over the past few years, couple of years, I guess. I have a 3 meter dish, and I've tried the ezRA software. Ran into a snag. So Ted, if I could, snag some time of yours to see where I might have gone wrong, that would be great.
I would be delighted to help. Maybe after this meeting, we can hang around. Thanks.
Great. Thank you so much. Yeah. So the basically it's a 3 meter dish. I've got a feed from Ham Design in the Netherlands, circularly polarized. So I'm looking at 1420. It's just a fixed mount at this point. I don't want to spend too much money on the mount until I get some signals going. But anyway, that's the information that I've got on the rig so far. Rich, thanks.
Well, great. Hope we can get that thing up and running. Are you on the listserv so you can ask questions on that?
No, I'm not. Maybe I should plan on that. I'll write that down. Thank you.
Yeah, I think Ted will put that link on. If by the way, that's sort of our 24/7 help desk. If you really want to think about it, everybody's monitoring that all the time and has no problem giving their opinion and help.
Yeah. Okay. Great. Thank you so much.
All right. Thank you. The let's see, Don Latham.
Spending more time with one of my other hobbies, which is making small holes in pieces of paper at some distance with rapid chemical decomposition, which is shooting. Anyway, nothing really new on the radio astronomy.
Okay. Thanks, Don.
Yep.
Bob.
Yeah, hello everyone. Good to see all the new folks and some of the folks that aren't here regularly. Enjoy hearing all these great stories. I got the opportunity to look over the upcoming journal, and there's a lot of good articles there. I think you guys that are members that get that will enjoy seeing that. I've been working on some software for analyzing my data from my magnetometer, and that's been my project recently. And other than that, nothing else to report. Back to you, Rich. I see Jeff Lichtman joined us here today. That's good. Hello, Jeff. So back to you, Rich.
All right, great. Let's talk magnetometer for a second, because some people think that's not radio astronomy, but I think it is. Can you explain sort of the information we get off a magnetometer?
Yeah, I've got a 3-axis magnetometer that came from the HamSci, through the HamSci group, that's going to be sold through the capper.org store now and in the future, I guess. And it's 3-axis, and you bury it in the ground about 3 feet down, and it's monitoring the magnetic field of the Earth. And the magnetic field of the Earth is affected by the sun's magnetic field and other factors. And particularly, I'm interested in the effects that are created by the sun, and analyzing and understanding what happens when you have flares and things of that sort from the sun, because it can create some pretty good havoc in the magnetic field.
All right. Anybody have any questions? All right. Thank you very much. Jeff Lichtman. Jeff? No. All right, I'm going to try Celsius. Oh, I think he's just listening too. All right. Did I miss anybody? Did we have a chance to talk?
Is that right? No.
I'm here.
Go ahead, Jeff.
I just want to say hello to everybody, and I thank you for what you're doing and heading up everything. And I'm looking forward to possibly seeing you sometime soon. I'm getting my my system back to do fast radio burst detection in the coma branches, and that's been quite successful.
Well, can you explain their system a little bit?
Yeah, it's a Spectra Cyber, and we have feed horns and the dish antennas, and I had been doing that prior to me getting sick, but I've resumed it and working with Dr. Ralph Boyd down in Mississippi and Carl Lister. So we're making some progress. I will send in a report sometime soon.
Excellent.
And thank you again what you're doing, buddy.
Well, thank you.
I look forward to hearing everything.
All right.
You're welcome.
Okay. Anybody have any questions for Jeff? All right. Okay. Final announcement is that we do have in this journal we have nomination, the official nomination notice going out for officers and board of directors. This round, the open positions are president, vice president, and I think 4 of the board members' positions are up for election or re-election.
Leave.
If you want to be involved in helping, that we really, we got a small group that runs this whole thing, and between Tom and we got the SARA Store with Lester, Chip does all of the web stuff and the web store. We have a small band that's been running this thing for years, and we can always use some help with, if you want to help, I can always sign you to committee, various other things that would help the administration of the SARA systems or the whole SARA organization. Anyway, just let me know if you need that. If you want to nominate somebody, please ask them first to be nominated, and then send your nomination to Bruce Randall, who's the secretary, or myself, and we'll get them on the ballot. And the ballot will be come out in the emails sometime before August, before the Eastern Conference. And then we'll have the elections for the next year's group. Okay. That's all the announcements. That's all we've got. Thank you very much. And remember, Drake's Lounge Australia is this Saturday, Melbourne time, 9 a.m. Okay. So it's a very good time for US time-wise because it's somewhere in the evening on Friday. So I'm going to send that notice out in the next couple days. The YouTube, this is being recorded, will be put on YouTube probably by tomorrow evening after I edit it a little bit and upload it to YouTube. And I'll send out a notice on listserv that this is up online. And so if you do look at any of our YouTube channels, it helps. They always say it helps the algorithm if you like them and subscribe, and if you actually make comments on it, it actually helps the YouTube algorithm. So that's just another little marketing pitch. Okay, that's all I've got. Thank you very much.